Today we will discuss one of the most important stages of the research process: data analysis, hypothesis testing, and interpretation. After a researcher has collected and organized data, the next challenge is to transform that raw information into meaningful knowledge. Data by itself has little value unless it is analyzed properly and interpreted correctly. This unit explains how researchers analyze quantitative and qualitative data, test research hypotheses, and draw valid conclusions from their findings. Mastery of this stage is essential because the credibility of a research study largely depends on the quality of its analysis and interpretation. Data analysis strategies. Data analysis refers to the systematic process of organizing, examining, summarizing, and interpreting collected data. The purpose of data analysis is to answer research questions and achieve research objectives. The choice of analytical strategy depends on the nature of the data, research design, and objectives of the study. In quantitative research, data analysis involves numerical information and statistical techniques. Researchers use statistical methods to summarize data and identify patterns, relationships, and differences among variables. Quantitative analysis is generally divided into descriptive statistics and inferential statistics. Descriptive statistics are used to summarize and describe the characteristics of a dataset. Common measures include the mean, which represents the average value, the median, which identifies the middle value, and the mode, which indicates the most frequently occurring value. Researchers also use measures such as standard deviation to understand the spread or variability of data and frequency distributions to report counts and percentages. Inferential statistics go beyond description and allow researchers to make conclusions about a population based on sample data. For example, a t-test is used to compare the means of two groups, while analysis of variance ANOVA compares three or more groups. Chi-square tests examine relationships between categorical variables. Pearson correlation measures the strength and direction of relationships between continuous variables, and regression analysis is used to predict outcomes based on one or more predictor variables. In contrast, qualitative analysis focuses on non-numerical data such as interview transcripts, observations, images, and documents. One common approach is thematic analysis, where researchers identify recurring patterns or themes within the data. Content analysis examines the frequency and significance of specific words, concepts, or categories. Narrative analysis focuses on understanding personal stories and experiences, while grounded theory seeks to develop new theories directly from collected data through systematic coding and comparison. Modern researchers use various software tools to assist with data analysis. Quantitative researchers often rely on SPSS, R, Python, Excel, and JASP, whereas qualitative researchers frequently use NVivo, AtlasD, Dedus, or manual coding techniques. These tools help researchers manage large datasets, perform analyses efficiently, and improve accuracy. Hypothesis testing. Hypothesis testing is a statistical procedure used to determine whether evidence from a sample supports or rejects a claim about a population. It provides researchers with an objective method for making decisions based on data rather than personal opinions or assumptions. The process begins by formulating two competing hypotheses. The null hypothesis, H0, states that there is no difference relationship or effect. The alternative hypothesis, H1, states that a difference relationship or effect exists. Researchers then choose a significance level, commonly represented by alpha, which is usually set at 0.05. This means the researcher accepts a 5% risk of incorrectly rejecting a true null hypothesis. The next step involves selecting the appropriate statistical test based on the research design and type of data. Once the analysis is performed, researchers obtain a test statistic and a p-value. The p-value indicates the probability of obtaining the observed results if the null hypothesis is true. If the p-value is less than or equal to the significance level, the null hypothesis is rejected. If the p-value is greater than the significance level, the null hypothesis is not rejected. However, hypothesis testing is not free from error. One possible mistake is a type I error, which occurs when a researcher rejects a true null hypothesis. This is often called a false positive. The probability of making a type I error is represented by alpha. Another possible mistake is a type II error, which occurs when a researcher fails to reject a false null hypothesis. This is known as a false negative and is represented by beta. The statistical power of a study, calculated as 1 minus beta, reflects the probability of correctly detecting a real effect when it exists. Researchers must also understand the difference between one-tailed and two-tailed tests. A A two-tailed test examines whether a relationship or difference exists in either direction and is generally considered more conservative. A one-tailed test predicts a specific direction of effect and places the entire rejection region in one tail of the distribution. Although one-tailed tests are more powerful, they should only be used when strong theoretical justification exists. Another important distinction is between parametric and non-parametric tests. Parametric tests assume that data follow a normal distribution and meet specific assumptions such as homogeneity of variance. Examples include the t-test, ANOVA, and Pearson correlation. Non-parametric tests do not require these assumptions and are suitable for ordinal data, small sample sizes, or situations where assumptions are violated. Common examples include the Mann-Whitney U-test, Wilcoxon-Sindrank test, Kruskal-Wallis test, and Spearman correlation. In addition to statistical significance, researchers should report effect size. Effect size measures the magnitude or practical importance of a result, independent of sample size. Common measures include Cohen's d, eta squared eta 2, and correlation coefficient R. Reporting effect size helps readers understand whether a statistically significant result is also meaningful in real-world contexts. Interpretation of data. Once analysis is complete, researchers must interpret the findings. Interpretation involves explaining the meaning of results, connecting them to research questions, and discussing their implications. While the results section presents what was found, interpretation explains why those findings matter. In quantitative research, interpretation involves examining whether hypotheses were supported, comparing findings with previous studies, evaluating effect sizes, and discussing confidence intervals. Researchers should consider both statistical significance and practical significance. A statistically significant result may not always have meaningful practical implications if the effect size is very small. In qualitative research, interpretation focuses on understanding themes, patterns, and meanings within the data. Researchers often use techniques such as member checking, peer debriefing, triangulation, negative case analysis, and reflexivity to strengthen the credibility of their interpretations. These techniques help ensure that conclusions accurately reflect participants' experiences and perspectives. Effective interpretation also requires researchers to place findings within a broader theoretical and practical context. Unexpected results should be discussed openly, and possible explanations should be explored. Researchers should explain how their findings contribute to existing knowledge and identify implications for policy, practice, or future research. Precautions in interpretation. Researchers must exercise caution when interpreting data. One common mistake is overgeneralization, where conclusions are extended beyond the population or context actually studied. Findings should only be generalized when appropriate evidence supports such claims. Another important precaution is avoiding confusion between correlation and causation. Just because two variables are related does not mean that one causes the other. Only well-designed experimental studies can provide strong evidence for causal relationships. Researchers should also acknowledge the limitations of their study. Limitations may involve sample size, measurement issues, time constraints, or methodological weaknesses. Being transparent about limitations increases the credibility and trustworthiness of research. Bias is another major concern. Researchers should strive to remain objective and consider alternative explanations for their findings. Presenting only evidence that supports a preferred conclusion can lead to misleading interpretations. Responsible researchers discuss competing explanations and explain why their interpretation is most reasonable. For example, suppose a study finds a statistically significant positive correlation between social media use and anxiety levels. A responsible interpretation would state that increased social media use is associated with higher anxiety levels, but it would avoid claiming that social media causes anxiety. Other factors, such as poor sleep quality or existing mental health conditions, may influence both variables. Case study illustration. Consider a clinical trial designed to evaluate a new medication for hypertension. The null hypothesis states that there is no difference between the medication and a placebo. The significance level is set at 0.05 and an independent samples t-test is conducted. The analysis produces a p-value of 0.03. Because the p-value is less than 0.05, the null hypothesis is rejected. The researcher concludes that the medication significantly reduces systolic blood pressure compared to the placebo. The effect size represented by Cohen's d is 0.4, indicating a small to moderate effect. From a practical perspective, the medication reduces blood pressure by approximately 5 millimeters of mercury mmHg, which may have meaningful public health benefits. However, the researcher must also consider limitations. The study followed participants for only 8 weeks and included adults younger than 65 years of age. Therefore, the findings may not apply to older populations or long-term treatment outcomes. Future studies should investigate the medication's effectiveness over longer periods and across more diverse populations. This example demonstrates how researchers should combine statistical results, practical significance, limitations, and future recommendations when interpreting findings. Conclusion. Unit IV represents the analytical heart of the research process. Through data analysis, researchers transform raw information into organized evidence. Hypothesis testing provides a systematic framework for evaluating claims and making decisions based on probability rather than assumptions. Understanding concepts such as significance levels, p-values, type I and type II errors, effect size, and statistical power is essential for conducting rigorous research. Interpretation is equally important because it gives meaning to analytical results and connects findings to broader theoretical and practical contexts. Researchers must avoid overgeneralization, distinguish correlation from causation, acknowledge limitations, and remain objective throughout the interpretation process. By mastering data analysis, hypothesis testing, and interpretation, researchers can produce findings that are credible, meaningful, and capable of contributing to scientific knowledge and informed decision-making.